Sure, sir.
Good morning, all. It's my pleasure welcoming our speaker, Dr. Shravana Kumar, our advisor, Dr. G. Samandan, and all the participants for the fourth day session of this STTP. I would like to request our advisor to invite and introduce our speaker. Over to you, sir.
Thank you, Dana. Good morning, everybody. Good morning, Mr. Shravana Kumar. It's my pleasure to introduce today's speaker, Dr. Shravana Kumar Musunuri. He is the team leader in Opal RT India. He holds a PhD in electrical engineering from Mississippi State University, United States of America. He specialized in power electronics controls, renewable energy. He has a master's degree specializing on electrical vehicles, modeling and simulation. He has over 15 years of experience in industry and research organizations. He has successfully led R&D teams in developing products and solutions, handled more than $750,000 worth of projects. He has 6 patents and 3 trade secrets and 15 plus international publications and presentations. With this small introduction, I hand over the platform to Dr. Shravana Kumar.
Thank you, sir. Thank you, sir. Thank you, ma'am. Good morning, all. Thank you very much for the nice introduction. So, yes, as sir was just mentioning, so I am a team leader at Opal RT Technologies. And today I'm going to talk about real-time simulation of power and energy systems. And this is my agenda of the presentation today. First, I would like to start off with, after a brief introduction, I would like to start off with what is the really need for real-time simulations. Just spend few minutes on it, and then actually talk more about the example applications of these real-time simulations, especially focusing on microgrids and on smart grid and cyber say physical systems security aspect of it. So this is where I'm spending more time on the example applications side. So just for as a very quick introduction, so Opal RT Technologies is a multinational organization with headquarters in Canada, Montreal. It has R&D and sales office in various parts of the world, as shown in the picture here. In Bangalore also we have an R&D and sales office. It was established in 1997. I think we are about close to 300 employees now, and with 500 customers worldwide. So this is an organization which is a leading provider of real-time simulators and also doing specialized energy services like helping people on specialized modeling or analysis aspects. So it looks like a small organization, but a very heavily focused organization with out of 300, probably about maybe 200 or more are electrical and communications engineers. So it is very heavily focused like that. So I want to start off with known stuff, but there is a reason why I have put the names, the titles also in this particular fashion. So the power network what we have right now is evolving. So the existing power network, on top of the existing network, you have more and more rooftop renewables which are getting added. On one side that's happening. On the other hand, you have the existing equipment which is probably put 15, 20, 25 years back. It is getting it is getting aged, so they need to be replaced or they need to be looked upon. At the same time, you have new type of loads like electric vehicles slowly are increasing, and one electric vehicle is probably more than few houses average load kind of thing. And you have metros which are coming up, which are big consuming devices. And you also have new type of load devices like intelligent and communication devices. So that loads which use these ICT technologies, uh, they they are fundamentally altering the behavior of how the user actually uses these devices. So its effect is happening on the load patterns. So what is the forecasted load, or the formulas that we used like maybe decades back, now that is fundamentally is changing a bit because of the composition of the load is changing, and the behavior of those people also is changing. So all this is happening on one side, and with this so many communicating devices and smartness coming in, so it also poses now a new threats, so which is in the form of cyber challenges. So cyber security issues, it is not widespread right now, but this is something that, it is a vulnerability. So this is something which needs to be looked into more detail, and that is one thing which is happening. And there is very new technologies like blockchain, where even power grid and other folks are also showing interest. So it's a futuristic technologies which has its own benefits, but again have their own challenges which needs to be looked into. So like this, the power network is evolving. The question is, how can we ensure, with so many things happening, so many new technologies coming and adding up, it is the power engineers are no longer isolated. So you don't have like a power engineer now, a computer science engineer, or a mechanical engineer, or so on. All these streams are getting together. So the communications, power, mechanical, everybody. So how can we ensure that the network is robust, safe, secure, and reliable? Now, that's always the challenge. So what is the one often used method? The often used method is to have a robust design and analysis methodology. So here is one example, so which is a very popular methodology, adopted, I believe, from automotives, but very pertinent and used worldwide now, which is a model-based design. So what is the need to have this model-based design? As the picture on the right shows, so any design that we make, or it can be a model, or it can be starting from the modeling side and slowly going to the design of the controls or anything. If we are able to find out the defects or issues with the design early in the early stages, then the um, hello, hello. Uh, I think somebody's mic is okay. Yeah. Um, so if we can able to identify these defects in the early stages, then the cost would reduce by 100x. So when we say this is a study by this one particular reference, a very old reference, but still very much applicable. Now, when we say the cost reduces by 100x when compared to detecting an issue or maybe a feature missing or something later in the stages of development, so 100x reduction will be happening, not just in the cost, I would actually say even in the time, even in the energy. So it is very important that when we start designing, when we start looking at a new thing or trying to do things, start looking at it more robustly with a complete holistic picture. That's what this model-based design gives. This I'm directly giving with taking microgrid as an example. I'm not going to spend too much time on this. It is just to will just take you through a glimpse of it. So if you look at it, any design, so if I take more microgrid as an example, it starts from the requirements. uh, what is the purpose for which I am doing that? Now a microgrid, uh, the purpose of having a microgrid uh, is, for each application it's different. For a defense application, for them the cost is not the main criteria, for them the reliability is the main criteria. Now, whereas for a rural application, the same microgrid, maybe they can compromise on the reliability a bit, but for them, cost is a very high. They want it to be a least cost. So cost is a very important performance metric there. So like that, so there is so be clear on what is the requirement, what is the main objective, and according to that, define your performance metrics. So that's what is typically at the start of the project, or anybody with us, the requirements, and then starts depending on those requirements and metrics. We start with the concept identification and system modeling, and we do the say, design of the studies or design of the system. Like for example, if it is in microgrid, we define the virtual models like the control model, the converter model, the power system network model, and so on. And we do some for the first level studies in terms of the is the load management. I mean the energy management if it's happening, is the power quality good and all that aspect. And then the typical methodology is once when it is done, you actually get it to the next level. So where you as a Lego pieces you keep keeping piece by piece in the sense that okay, now that my design is good, let me put my design in a controller and test that controller. If the control if it is working fine, then let me go to the next level, maybe put it in a laboratory set of environment and check if everything is good. If that is good, let me integrate different pieces and everything is good. Then finally go to the field testing and so on. This is a very standard model based V curve kind of approach. Now the reason I was showing this is fundamentally, if you see there are I wanted to focus on this word called real time simulation, which is this gray curve or the gray piece of this V curve. So if you see, um, right from the design stage, the typical method is when we what we call when we say offline studies, we do something in the computer and then we directly get it onto the breadboard, onto the controller outside and test it. Now when we do it onto the controller with all our best capability, we design it, but there are many pieces which we miss in. Like some of the pieces would be system on the field. It is a multi-system multiple processors, so interaction between those multiple processors, so we don't really capture that. So whatever controller that we design, not necessary that it will work in the same
Sir, your voice is breaking actually in between.
way as it was. Is it, madam? Okay. uh one second now.
Hello, Dana.
Hello.
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 Dana, I think you got to mute others. I think there's some interference is there.
Now, sir, I could not hear. Is it? I could not hear actually.
No, now it is okay. Now it is.
Okay, okay, sir. Okay, fine.
uh, are you able to hear me? I can hear you.
Yeah,
Uh,
I hear you.
Now it's clear, sir. Now it's clear.
Okay. uh okay, let me come a bit closer to uh my wife, I think so. uh, okay, I will. So you are able to see my screen also, right?
Yes, sir. Yes, sir. It's in the
Okay,
model-based
so
design.
yes,
Yeah.
yes. So okay, so basically, so what I was saying is uh, yeah, so the in the model based design, so it's a very standard thing. So the real time simulation represents the gray part of it, and fundamentally what it does is it addresses a key aspect, which is in the design. Many times we are not aware until a certain stage is reached if the design will work in the real field or not. Real time simulation addresses that aspect. So that's why I said like I'm going to cover this very briefly because this in itself is a big topic. So fundamentally, so what is real-time simulation? So here in a pictorial or graphical form I can show. So there are here on the top we have what is called a real clock. So the atomic clock on which all the the entire processors everything works, the real clock. And so for on the left hand side is what I call the desktop simulation. So what is desktop simulation? So you would have experienced, say for example, MATLAB Simulink or anything. So when you actually make a model and when you try to simulate it, depending on the complexity of the model, uh, sometimes even if you say 10-second simulation, the entire simulation might take the simulation time might be 10 seconds, but it might simulate for 1 hour because it takes so much time to do it. It's limited by the processing capability and also by that particular software. Sometimes for some particular models, for a 10-second simulation gets done in probably less than half a second. So that is what I mean. It's more like it's like a desktop. It's a desktop simulation. It is not working as per the how a physical device would work on. And that is what real-time simulation does. If you can see in this picture, the real-time simulation, it simulates exactly in coherence with the real clock. So if you say in the simulation that, okay, I have a relay, that relay should open at 1.2 seconds, and it should be open for say 20 milliseconds. And when you simulate it, it simulates as if it is a real device. So exactly at atomic time clock of 1.2, it opens, and for 20 milliseconds, it works, and then it closes. So that is what is a real-time simulation. So a real-time simulation is not necessarily very fast. Again, so it is an embedded systems definition. So many people think that a real-time simulation means as I talk, it should happen. It is not like that. It entirely depends on the application which is being targeted. It should be fast enough. Like for example, if for electromagnetics applications, we are interested in microseconds or maybe sometimes nanoseconds. So that is real time for that particular kind of studies. Now, versus if I take a temperature thermostat kind of control, then microseconds, milliseconds does not have any impact on it. So the region of interest there is on seconds. So real-time simulation for those applications like in seconds. So to give a bit more detail, so a real-time simulation must accurately produce these internal variables and outputs within the same length of time as its physical device would. So if you take any system, so if I say a simulator, if I want to understand its response, it has three stages. It takes the input, computes it, gives the output. So all these three stages should be done in one time step. So if we take a model whose time step is like 1 microsecond, for example, within 1 micro, all these three stages should be done. Now, here are three different ways how it can be done. If I start with a real time thing, so here is the time horizon T represents the the time step, the discrete time step. So if I have a task which starts at this time, but it gets completed, the task gets completed even before the next time step, it does not start off the next task at this instant itself. It will wait for the next time step. Why? Because that is how a physical device also would behave. The physical device is a digital system. That's how it would behave. Now, when compared to this, if I take a offline simulation where the same example, the task is completed here. Now, for a faster than real time, so kind of case where as soon as the task is completed, it will take on the next task. So that's if you see, like, it is actually working much faster than real time. It has its own advantages where you can do larger scale simulations. It's much quicker, but it's not really a true replica. Now, when compared to this, now you also have a slower time where you the task sometimes takes more time than the selected time step. So what happens? So what we call the overrun. So it exceeds the next time step. So the task is completed, but then it waits for the next time step. So so some pieces are missing. So that's so that's what this third one shows, the real-time simulation, which is one aspect of real-time simulation, which is get synchronized to the real clock and try to behave as close as possible to the physical device would do. So very quickly, what are the advantages? Fundamentally, it is used to reduce the risk and the cost. In what way are we reducing the risk? Basically, the risk in terms of the equipment damage, or risk in terms of the time, energy, and of course, cost is also included in that, because we are validating at each step of the design through real-time simulation or to real-time performance. we can we know that as we move forward in our design or development, we know that whatever I'm developing, even if I put it onto the field, I can expect a much very close behavior uh, of what I'm trying to do now, especially when compared to the offline simulation. So that's the fundamental benefit, and it helps in giving an opportunity to analyze various scenarios and helps in taking corrective actions. When I say corrective actions, so okay, if I have a when I'm at a particular design stage, I see that the communication delay is impacting my controller performance. So I can immediately go back, tune my controls, and come back instead of waiting, going on to the field and then going back to the design. So that's fundamentally an important thing, and it gives a visibility of how the network would behave actually in physicality, and that's what we are trying to do. And the third, and this is a point where I am actually going to spend my examples also on, is it helps in creating the test bed, especially for power systems kind of applications or cyber systems kind of application, where it is not possible to create a fault in the power grid and see what is happening, or you cannot ask somebody to hack into a power grid and see, and show that it is possible. So how to mimic that entire scenario? Now when we say mimic, it has to be a realistic mimic, otherwise the study does not have a meaning. So how to mimic that is what is one of the major benefits of real-time simulation. So where is it useful? Very quickly, it is fundamentally in the last 30 years, it was applied, I believe, in all aspects of power. Of course, it's applicable in automotive and those things also. But speaking mainly from the power side, I think it's applicable everywhere. So it has multiple variations to it. So if I start with a very basic building block, there are three basic building blocks for any system. You have the plant, you have the controller, and you have the sensors. So which sensors are communication equipment and all that. So now for a second, if you think, if you keep the sensors also as part of the plant, basically you have two main systems. So you will have 2 into 2 4 variations of how this scenarios or systems can be. In one variation, this box is what is a real-time simulator. I'm going to talk about it in the next slide a bit more. You have your entire plant, controls, everything embedded into this box, which is like a high performance computing box. And what we do, we have something called a software in the loop, where you have entire design put inside that same box, and through virtual interfaces you have the plant connected to the controller in a virtual form, and the device under test connected to the controller in a virtual form. So you do an in-loop testing there, software in-loop testing, which helps you in understanding the impact of any the IOs or any communications in a software environment. The next variation is where you take one of the pieces. Say for example, I'm taking my MicroGrid controller, I keep it outside, which is say device under test, but the rest of the plant, everything is staying inside this high performance box. So you have this box, the real-time simulator keeps interacting with this device under test, which is a controller, and you can test how well this controller, which is a physical device, interacting with the simulator. The simulator now behaves like a plant because it's a real-time simulator. It responds in a same way as how a actual real power grid or power network will behave. So how this controller is interacting with it in real time, we can study that. That's what is HIL. Yeah, the same thing probably in a slightly varied fashion, where you have in a lab environment, you have all the motors and the panels and solar panels and the wind system outside, but you want to you can use this thing as a controller as well. So where you're trying to test the impact of the controller, so you can embed the controller code inside this and interface with the physical hardware and see. That is called the RCP, rapid control prototyping. A slight variation to the HIL is the case called power hardware in the loop, where we have many cases where since these are electronic devices, at the end of the day, they are restricted by the power that gets transmitted between these two devices. So that's why we have something called a power amplifier. So for cases or examples where we want more power to be there, so it is interfaced through a power amplifier, which helps in connecting a a slightly larger power levels, like say 15 kilowatt system or a 20 kilowatt, or maybe in some cases even up to 200 kilowatts also. So these are the different scenarios. Uh, so what is a real time? How does it look like? What is there inside that? I wanted to touch upon it for 2 minutes. So this is what is an OpenRT's real time simulator. Fundamentally, uh, a a real time simulator, you can think of it like as a high performance computing machine. Okay, it fundamentally has three main pieces to it. One is the computing element, which is the processor. So a typical simulator will have two kinds of processor. One is the CPU, central processing unit, what we have right now, and the other is on FPGA based processor. Now CPU has its own advantages and I won't say disadvantages, its own limitations. Like it is very good for applications where the the sample time or time step that we need is from 10 microseconds or more. So you can put a much bigger systems into it, but it is a, I would say, in relatively restricted by the time horizon. So it can do 10 microseconds or more effectively. Or I would say the speed of the operation is bit slower when compared to an FPGA, where it is fundamentally designed and tuned to operate at much higher frequency. So you can go to 250 nanoseconds or maybe much smaller time steps, or so such a high fast updates and simulations are possible. So this is one of the important aspects of it. The second is the drivers which define the communication, the internal communication between these various various subsystems of a simulator. The third thing which is important is the interface. So this simulator should be capable of whatever be the simulator. It should be capable to interface with the outside world. So these are the three pieces which are always important for any simulator. Now, if I take this as an example, um, so and if I take a microgrid as an example, here I am showing. Now I have a microgrid network where the power system and the rest of the plant and other stuff, I can happily put it in a CPU environment, because the dynamics of that, again, we should be clear about what is the objective that we want to do. In this case, I'm interested more in the energy management or power quality, and I know that I don't have a 100th harmonic or something. So so at the max I have maybe like a 20th or 30th harmonic, that's it. So the I can happily keep this, embed this entire power system network within a CPU environment. But there are some subsystems, like for example the controllers, the especially the solar inverter controller and the wind controller. So these are very fast acting devices, so I want to effectively capture the each and every pulse. I don't want to miss on any pulses. So for those I would actually embed them into an FPGA environment, so you can automatically allocate which one goes to CPU, which one goes to an FPGA. There is also a case where, for there are many studies where people would like to study the machine dynamics, so which are many times at sub microseconds. So those also can be put inside the FPGA. So as I'm showing on the top here, uh, these are some of the software which are available from Opal RT. So as the HyperSim, eMegaSim, ePhaserSim, these three software, they are fundamentally designed to work on phasor analysis or EMT kind of studies. Uh, ePhaserSim, as the name says, is mainly tuned for phasor analysis. We are looking at 1 millisecond, 10 milliseconds kind of time steps, but looking at 100,000 nodes, 1 lakh nodes, 2 lakh nodes kind of big, large area, wide area kind of studies. Hypersim and eMegaSim are more focused towards, like I have 3,000 buses, a much smaller power grid, 3,000 buses, 2,000 buses, or maybe 50 buses or anything, and which has a mix of controllers and power electronic controllers and power equipment and so on. So it helps in so the requirement there is, I want to do a study at lower time steps like 10 microseconds and so on. So that's where these two are used. Now EFPG, as the name says, like for applications where I want to go to a very high uh, frequencies, 250 nano or maybe much lesser than 250 nano. So no, that's where these are. So these are the there's a product, and these are some of the software and how they are applicable to depending on what is the application in target. Now, as I was saying earlier, so any simulator should have an interface to the outside world. So now it can be a inverter controls or anything like what I was talking earlier, the for the HIL kind of setup, or for power systems or for cyber smart grid kind of studies. It should be capable to interface and integrate with the existing SCADA or the protection systems available uh, in the substation. So that interface is this uh, these ports actually enable that interface. So this is how it looks like. Now, um, are you able to hear me, madam? Hello.
Yes, sir. We're
Okay,
able to hear
okay.
you.
Yeah, I just wanted to
Yes,
check.
sir.
Yeah.
Yes, sir. Yes,
Okay.
yes.
So uh, now I want to take only one slide, like maybe spend 2 minutes on this particular slide. It's on a it's basically my observation when I interacted with many people over the last few years, and I thought it's very good to mention it again. It might be very obvious, it might be like a engineering 101, but believe me, this is the place where 90% of the issues actually start coming up. And that's why I just wanted to say general rules of thumb for modeling, particularly on the time step selection. Uh, so uh, it's known thing, but I wanted to re-emphasize again. So the time step selection should always be based on the highest frequency component of interest. Like for example, if my frequency of interest is uh, let's say 2 kilohertz, as I'm giving an example here. So I want to effectively capture and understand a 2 kilohertz transient phenomena. Then the suggestion is take 5% or 10%, the 10% of that as a sampling time step selection. So for a 2 kilohertz, maybe we'll end up with 25 or 50 microsecond to effectively capture that transient. Why am I mentioning so much about this? It's a very known stuff, but quite often I have seen in many papers where I see somebody tries to capture a harmonic of fifth harmonic or 11th harmonic, but they have a time step of 1 micro or zero point 0.1 micro. And I also see some papers where they try to capture again a load which actually varies at a much lower frequency, if not a load or maybe an MPPT or something, solar and MPPT, but the sampling is so high that the algorithm gets confused. Like so, select the time step in accordance to what is your objective. So there are some studies, like say if you are interested in transient recovery voltage, which is like voltage across a breaker, circuit breaker, then they are a fast acting phenomena. You might have to go till 2 microseconds, 4 microseconds, because they are at a range of 10 or 20 kilohertz. Now, within the same power systems, there are also something called a very fast transient over voltages, which happen in a GIS substation, majorly used for GIS substation studies. So there you need to probably go to nanosecond. Like I was doing a 2 nanosecond, 5 nanosecond kind of study, because it happens at megahertz scale. So it's depending on, even if you are saying a power, I'm doing a power system studies, depending on your objective on your study, please select your time step accordingly. Now, especially when you have converters, voltage source converters, or this kind of things. So I would say go a much smaller time step to effectively capture those pulses. So perhaps maybe you can go till 0.2% or 1%, again depending on the memory restrictions and all that. So I would suggest go till 1%. So for a 1 kilohertz, if you really want to get a very high precision resolution of your design, so that you can be sure that even when you put it onto a field, that you are able to capture everything well. So I suggest go till 1%. so that you can effectively capture all those pulses, and all the quantization and everything also can can get covered into that. Uh, that's another thing. Now, one of the fundamental things what I observe is uh, when we actually do the design, especially for feed, when we have the feedback controls and everything, when you have a very slow dynamics, that's okay. Like for example, when you're trying to do a power system stabilizer or something like that, so or an exciter and so on, the dynamics are in terms of seconds. So the sensors or the the latency between the hardware and the computer is inherently captured. So we are not we don't have to worry about it. But if you have a microgrid or maybe a communication network or such kind of studies that we want to do, then you have to effectively capture the latencies, the IO latency between the hardware and the computer. Why? Because when you put it onto the real field, that's what it sees. Now, I see many people that they do the studies very well, they select the time step very well, they do everything perfectly, but they either forget to put the sensor, the sensor delay or the communication delay. So that ends up in sometimes it will not do anything harm when we go to the field, but sometimes it does create a harm. Why? I'll show you one example. Here is a fictitious example, but I have a real example also from one of the customers, but I do not want to show that. So um, it so if you see, the blue curve is the base case. So everything here, everything looks good when it was designed on the computer. Now a 15 millisecond latency is added. That latency can come because of any aspect of the communication, but it was added. The moment when a 15 millisecond latency was added, you can see there's a lot of change in the response. Now for some applications that response is okay, but for some if I'm a protection relay guy and if I'm very interested in looking keenly at that, for me this is a very big change. So that's why, so please be aware about that. And um, yeah. Now, so that's, I mean, I just thought, in the interest of, especially when I talked so much about real-time simulation and so on, just remember, so a real-time simulation it's an enabler. It helps you to design stuff more robustly. But again, at the end of the day, we have to make sure that we understand what is its requirement correctly and also put in places accordingly. So we have to put a proper model into it, because at the end of the day, whatever we give in is what it comes out. It's a box. It is the humans which have to put more focus on to, are we giving the right inputs to it. And one of the right inputs is the selection of the time step and so on. That's the reason why I was a bit emphasizing on that. So now I will come to some we have I'm not going to talk about many use cases. I have like probably about 30-40 use cases, but what I would like to do is I would like to spend some time on 5 or 6 use cases that we have and talk through it, so that you will get a glimpse of both from the cyber physical system side, the smart grid side, and the microgrid side, and so on. So let me start with the um, microgrid Lincoln laboratory. So as I was saying earlier, one of the main applications of this real-time simulators is to uh, develop a test bed. That test bed becomes an enabler to perform multiple studies robustly. So if you see what is happening, like earlier, in my earlier company, I used to work in another organization where we were the OEMs for microgrid controller. So every OEM of a microgrid controller would say that my controller is the best, naturally, and it has a lot of functionality, it has a lot of features. But we are not talking about a mobile phone where a person can really use it, test it, and give it back. We are talking about a power grid. We are talking about something uh, whose uh, whose applications are slightly different. For defense it is different, for rural it is different, like that, and whose functionalities and features are coming up. There is it is more customizable one, right? So how do we test or in the sense that how do we validate that, okay, this particular controller is suiting my needs, and this particular controller is probably not suiting it, or I would like to have these features, because these are heavily customizable products. So in that regard, MIT Massachusetts Institute of Technology, along with the OEMs like Schneider, Eaton, Opel RT, and Woodward, and SEL and others. So they thought, okay, we have to make a test bed, a generic test bed, so that multiple scenarios can be defined and tested in that. So what happens is, like, then you can benchmark the performance of each and controller, or maybe it helps in even defining the requirements for the distribution companies. Like, even they are not completely aware what is the requirement, right? So that is what this micro MIT Lincoln Laboratory MicroGrid lab setup. I know it's a big name, but that test bench does it. So the intention was to come up with that vendor neutral test bed so that people can analyze that. So if you see here, what does it have? So it fundamentally has the Opel HIL target. So when I say target means a simulator. The simulator holds the actual power network that is under study. So here for this test bed, they have selected something called a Banshee distribution network, which is a real network. Banshee somewhere in the United States. It was selected and it was put. So that network was modeled and put in Opel simulator. So moving forward, that simulator would act as if it is a real power network, right? So yeah, so that target interacts with of course, has the interface boxes. So through the interface boxes, it interacts with the various other subsystems. So what are the other subsystems that we have? We have something called a diesel generator. So the diesel generator, the photovoltaic inverter, and the other hard systems, they're all modeled and kept inside this Opel RT simulator. But their controllers, like for example, what I'm showing here is the Woodward controller, controller which controls the diesel genset. Uh, in the SEL relay, which actually helps in shedding the loads, taking the command from controller and so on. So those relays are actually the hardware devices. So this interface box and helps in interfacing the real power network in the simulator with the actual hardware devices. And of course, you have the network switch and other communication devices, which helps in interacting with the microgrid controller. So if you go back and if you see the complete test bed, you have the real-time simulator interacting through this IOs, through this interface boxes with the say for example, here we have the eco power inverter controls, and you also have the Schneider Electric's microgrid controller, the central controller interacting with the solar inverter controls and so on, and also with the relays. So this essentially is that test bed. So tomorrow, this Schneider controller was replaced with Eaton's controller, and the same set of scenarios were made, and it was seen similarly for with ABB and so on. The intention was, okay, now I have a test bed which is used to do this test. So they first did the offline studies, and then sorry, and then a real-time study was done. So not going into very great detail, but when the offline studies was done for a particular load shedding case, like one particular at time t is equal to 7.8 seconds, there was a load shed command that was given by the controller, and it was observed how the frequency variation happens. It was observed that in offline simulation, the frequency actually drops to 55 hertz. Okay, yeah, in one particular scenario. Whereas the same thing when it was tried to replicate in a real-time environment, the frequency drop was not that bad. It was dropping till 56.3. Now, why is that? I mean, it is because the system is responding much quickly. So the controller started sending its information, the data to this simulator. The simulator is doing it much quicker, and it is sending back to the controller. The response itself as a system, as a physical device, is much faster. So in this case, it was shown how you can see the difference between in performance in offline versus a real time happened. So like this, multiple scenarios were developed, and like black start was one of the things that was developed. Load shedding was one of the things which was load shedding was one of the things which was tested, and so on. So this has become like a I would say a test bed for future studies. Yeah. So excuse me, I'll just want to drink water for a second, madam.
Yes, sir. Yes, sir. Yes. Carry on.
Yeah. Hello. Hello.
Yeah,
Yeah.
yes, sir.
Are you able to see my screen also, madam?
Yeah, yeah, yes, sir. There's another example.
Yes. Yeah. So this is the example on which I want to spend more time on, a lot of time on. So what is the reason I gave the above example was it's a very straightforward microgrid test bench, which is used for typically understanding the from the as a power engineer's perspective. Okay, so is the controller meeting my functionalities, black start, load management, frequency study, response, and all that, which is good. But as I was mentioning earlier, uh, one of the things that happens uh, with so many new technologies, especially the information and communication, all these technologies which are coming in, is we have to be careful about the network, the power network safety, security. Right? I mean, there's a chance that somebody might hack into it, might create some, unwarranted things. So on. So, how do we do those studies? And what is the kind of setup we need to do those studies? And so that is what is cyber physical systems research is one topic over the last, I think, decade or so has gained a lot more prominence. Like it is in that aspect as well, like where the real-time simulators can be very helpful. Why? Fundamentally, we are talking about a real-time communication, a real-time hacking somebody on changing some things on a real time, and it's if that gets changed, what happens onto the network? So. Uh, See, I am a power engineer, so I am not into much into the network or computer networks or the network side of it. But if I look at more as from a um, power systems perspective, I have five the power systems hierarchy. The entire operations of a power systems can be put into like 5 layers. On the human layer, we have you know operators, the people who operate the power operations, the grids, and so on. And on the application layer, so we have what have ultimately what we are doing right now. So whether it is the discom doing an energy ems kind of study applications, the energy management, or the SCADA applications, and all those things come under the application layer, the studies that we want to do or the things that get done. And you have on the communication and network layer, so all the different communication infrastructure, the protocols, and so on. On the below layer, the controls and actuators level. So these are the actuators. These are the devices which actuate a response, or which gives the data to cause a response. So they are the relays, the PMUs, or the controls or the controllers of the respective things. And then you actually have the physical layer, which is the physical devices, uh, generators and transmission lines, inverters, and so on. So from a power engineer's perspective, when we look at it, this is how it would appear. Now, uh, there's one thing which I wanted to point here. So uh, OpenRT or myself, we are more power guys. We are more power systems, electrical communication, but more into electrical kind of studies level. Uh, so we actually partnered with our partner called Scalable Technologies from uh, California, Los Angeles, US, and they are more into the network, the computer networks, kind of in the hacking, the cyber aspect of it. So we both together found that there is a gap of this kind of studies are needed, but there is no a foolproof or a very good infrastructure in place to do that. So together we have actually developed what is called this co-simulation platform. Why do I call it as a new co-simulation? Because there were two architectures we had in mind. What I am showing is a much I would say advanced architecture. It has its own major advantages, which is there are two essential systems, right? One, you have the physical system, the power grid, which needs to be modeled. Okay, and also you need to you have the communication network, the communication system in the outside world. Like for the context of this entire thing, if I take a power grid or a microgrid for as an example, so a hacking can happen on a power network, but it happens through a communication network. So you need to model both of these things effectively and robustly. It is not sufficient if you have a very good model of a power system network and you create a hypothetical scenarios for a communication network and say I'm hacking, because that's not how actually it gets done in the if it's a purpose of having these studies. On the same way, it makes no sense if you are only a computer networking engineer, you develop a fantastic hacking algorithms and come up with a hack, but you are not able to understand or integrate it to or study or interface it to a network and see. So that's why, so in a sense, you need to model these two things, two parts of the system, physical grid as well as a communication network. Both these models are modeled in this platform in one simulator box. So how we are able to do it? Fortunately, many of this the real-time simulators, these, as I was mentioning, these are high performance computing machines with multi-core architectures. So many times we have 4-core, 8-core, 16-core kind of systems. Um, so here in this example or in this picture, what I'm showing is on the core 1 and 2, you have the physical grid which is modeled. I will take you through an example as well. And on the cores 3 and 4, you have the communication network which is modeled. Okay, and these two models are kept it in two different cores, and they are linked together through virtual links. Now it has its own advantages. Even though they are virtual links, the beauty about that is you can program it in such a way that you consider the real the communication delays or anything what you want, you can program it to behave it like that. So essentially with much lesser hardware, you can reprogram it and you can use it for different kind of applications that you want to do, or different kind of scenarios that you want to create. So this simulator box, this entire thing which all that with all that um, interfaces, so there is a host PC. This host PC at the end of the day is what controls this simulator, I mean, as a GUI and also as a controllability aspect. It interfaces through one of the Ethernet ports, and with the other Ethernet port it gets connected to an external controller. I mean, it has a capability to connect to an external controller. Again, it can be a MicroGrid controller, it can be a tap change transformer controller, or a relay, or anything. So this is one co-simulation platform where in one environment itself we are, or using one simulator or one environment itself, we are able to co-simulate or model and co-simulate both this power grid and communication network at the same time. And the other architecture what I was mentioning about is you can also have, instead of having only both put at the same simulator, you can actually put the entire power grid in one simulator and the communication network in another simulator. And also so you basically have two simulators in thing. That's also possible. That was our first architecture. It has its own advantages in the sense that you will get a lot more flexibility. But again, what we understood was that this architecture is because it's a reprogrammable one through the virtual links. It is good enough to study majority of the studies we want to do. Now, before I go there, so um, the I think I'll come to the next point. Okay, so this the, we have talked about the power systems modeling and network and have shown an example of that in earlier slides. So the communication network, so made by Scalable and applied together, it also has a sorry, the communication network made by Scalable, but together along with Opolarity, what we are using is it's called the EXATA EXATA Cyber Physical System uh, model or system. So here is the GUI which shows the real-time network state. So I mean, this again is an example. Uh, on a map or a terrestrial kind of map, a GUI which shows that you can actually control, okay, I want to create a scenario where I'm reducing the load here, or I'm introducing uh, a an intentional hacking through a tap change transformer, or through a interfacing a controller. You can actually control all that through this GUI. Now, how is that possible? How we are able to control through that, or how is it defined? This is how actually it's defined. So let me take as an example. It will be much easier to explain through an example. Here is a microgrid example that I would like to take. It is basically a 120 kV system connected to one distribution feeder with it has multiple DRs, it has a CHP system, a 10, and actually the main system which is responsible to ensure the energy changed to meet that to make that energy balance. And we have two PV systems, 1.5 megawatts each, and of course they are running at the maximum power mode always. And they have their own battery to smooth out any power. And we also have battery energy storage system. So as you know, it is majorly used for energy smoothing out, right? So it's majorly smoothing out any variations which happens because of the imbalance. Minute scale, or sorry, second scale power imbalance happens because of load changing or solar power changing, and so on. And that's what the BESS battery energy storage system does. On the load side, we have particularly we are showing some building loads as L1 and house loads, and so on. Now, the priorities was given for each of these loads. So like the load 1 and 2 are called the critical loads. Like for example, we can take it as a hospital and maybe a factory. They are like critical loads, so that means they always have to be connected to the system. There are no exceptions. Whatever happens, even when there is a utility failure and it goes to islanded mode, it has to be connected. And you have a Load 3, which is on a priority basis, can be connected, disconnected depending on the energy management and that particular scenario. But you have a load 4, which is this one, which is defined as a non-critical load. Now, one point which I wanted to mention here is this non-critical load. So when it, if the scenario was created in such a way that when actually the system goes into an islanded mode, we want this non-critical load to be disconnected ASAP, that is as soon as possible. Why? I mean, the situation was created in such a way that if it is not disconnected, there is a frequency deviation, frequency instability, and the frequency instability keeps on increasing the more time it takes to shed the load. So that is how the scenario was created to demonstrate this entire thing. So once again, it is very critical to shed the load for as soon as an island is detected. Okay, so this is the what do you call this is the topology that I would like to take to explain this in detail. Now, um, uh, yeah. So how are these different things which are defined in the virtual environment? When I say we had the co-simulation platform, how are all these things defined? So IED is a virtual IED. Virtual IED was created for each of um, the DRs, or I would say each of the devices. Like for example, for PV, wind, battery, loads, everything, a virtual IED was created, and uh, and they were defined, they were created, defined, and interfaced through the to the communication network. And you have sorry, one thing I forgot to tell here, the important thing, which is the microgrid controller. Sorry, this microgrid controller, it through a network switch, I think I had the slide. No, sorry, I thought I had the slide. Through a network switch, this microgrid controller receives information from all the IEDs. So you can take this red dot as an IED. As an example, it takes information from all these IEDs, determines, what is the at a second by second level, what is the ensuring the load and generation gets balanced, and takes the necessary control actions. So that is what this controller does. So so basically we have three levels defined on the station bus or at the station level. uh, we have the microgrid controller. So the microgrid controller interfacing through the network switch to the at the bay level to the IEDs, the virtual IEDs which were defined, and these virtual IEDs they actually interact with the at the process level with the uh, the models of the PV, wind, and other systems. So 2 points here. One, this red dot here shows the communication infrastructure made in that EXATA CPS, which helps in interfacing between uh, which is not helps in interfacing, but which is used to do the the cyber hacking and kind of studies. The rest of the system is the rest of the system is put in OpenRT's tool called HyperSim. So basically, the red dots is put in the communication software called EXATA, which provides capability to do the hackings and all that. And the rest of the system is modeled and put it uh, in a power software called HyperSim, which helps in interfacing with that. So yeah, this is the example that sorry, this is the picture of the model. So so as I was mentioning earlier, so it is HyperSim is it's like an electromagnetic transient program, just like EMTP. So which helps in power systems and power electronics analysis, but has the capability to perform to do real-time studies and analysis. So it is not just an offline tool, just with a switch of a button, we can actually move into real-time mode. So here in this model was made, this microgrid model, what I was talked earlier, and a goose ID was created for a goose ID was created for each of these things, and the appropriate Ethernet ports were identified, and as you can see, it is all very easily definable in this tool. So it was created and it was interfaced to that network. Yeah. So I think this is again the same thing. So this was what I was showing earlier, but this was the EXATA, the screenshot of how it looks like in that EXATA network software. So there are some command, the different types of attacks are predefined in that. So depending on how we define the IEDs, the node of those IEDs and how they're interfaced, so the different types of attacks can be just selected, and we can do at which node. That means at which particular node, what type of attack we want to do, and what type of manipulation we want to do. That thing was is available in this particular software. So we basically take advantage of that and study that. So I'll show first scenario. Now we can always think that okay, um, my intention is not to go into detail about that particular software or how it does the hacking and all that. That in itself is, first of all, is a very deep thing. It's a one full software, but more importantly, my interest is to show what is going to happen. Why is it so critical? What are some of the challenges or issues that comes up? Now here is one case, right? So as I was mentioning earlier, the entire microgrid was designed such that this load 4. So when a fault happens and when this disconnect switch opens up, we want that is the energy was, or the balance was created in such a way that the load 4 has to be disconnected immediately. Otherwise, you have a case where you have the load more than the generation. A scenario was created like that, and there is a system will slowly go into the instability mode. Now let's see what is first hacking or first kind of thing which was done. Assume I am a hacker, or I intruded into that particular network. What I will do is, okay, I understood the logic. Okay, that as soon as a islanded situation comes, the load 4 actually should should be shed. I've intentionally, I have added a little bit delay in sending the command from the microgrid controller to the load 4. So I've just added a little bit of delay. So if you see how what is going to happen now, the blue lines shows that okay, when a fault happens, everything looks good. There is when there is no delay, the voltage and the frequency are maintaining at 60 hertz, and it's everything is good. Particularly, the region of interest here is the frequency. Okay, now if I add a 0.5 second delay, if I am the hacker and if I just intentionally add a 0.5 second delay, I would talk more about the frequency because that's a very important parameter to observe. You can see that the frequency deviation, suddenly because of that 0.5 second delay, which a hacker added, you know, in real time, the frequency variation has increased. Now, if I add a 1 second delay, so the microgrid controller observes island, it happens, it detects it, it sends a packet of information to the load 4, but the intruder added a 1 second delay to that packet of information. You can see the frequency excursion. Just because of that, the oscillations increase significantly. Now, why is so important? I mean, you can still say that it's only 62, say 60.7, but if you see, the important thing there here is the protection elements were defined, will always be defined in power grid in such a way that beyond a certain level of frequency deviation, they will trip, right? So in this scenario, if you see, the protection relay is going to trip because it sees that there is a lot of frequency variation and it trips that. And it's not just that load, it depends on, okay, since the frequency is a common component, it trips for the other loads as well. So that's how you can, one of the ways, potentially somebody can just hack, do nothing, just add a delay and cause a perturbation in the system. Let's take another example, which is uh, uh, you know, which is again, which is more on the energy management side. So if I take, even though the example is microgrid, the same thing would be applicable to the, I would say, I won't say the complete power grid, but the philosophy is the same. Like when the system isolates, the microgrid controller ensures that, okay, on the one hand, the load force should get isolated, disconnected, it gets disconnected, but it has to make sure that the generation and loads get balanced. So what does it try to do? Um, uh, it it controls the generation. In this case, as I was mentioning earlier, the CHP, the combined heat and power generation, is the entity responsible for ensuring the generation and load balance. So it increases its power to meet the load. If the load is still not met, then it sheds one few more loads. Okay. Now, how does that happen? If I go back to this again, sorry, I had to move back and forth. So how does it happen? So the microgrid controller always keeps track, taking the information from each of the IEDs, and does that second by second level. Okay, the what is the power which is flowing through each of these devices, and what is the total load I have, and all that, and then it does its algorithms of EMS application and gives the necessary set points. Right now, here in the second one, what I do is I have a one particular type of load. Again, it is load 2, which is probably a factory load. Uh, so the load, you can assume for now, the load might be a constant power load, but uh, what the intruder has done was that the bytes 113 and 114 represent the the virtual IEDs of that particular load 2. Sorry, uh, it measures the power information of the load 2. The power of that is coming through bytes 113 and 114. The intruder wantedly multiplies with a factor called 2. In essence, what the intruder is saying is I have a lot more load power, lot more. The load 2 is lot more than what it is actually. So that information goes to the uh, microgrid controller. So it sees that okay, the load is more than it starts immediately thinking that okay, the load 2 is lot more. So the generation has its own limitation. So what does it do? It thinks that okay, since the load is very high, it shuts the load 3 as well. Why? Because the load 3 is also a non-critical or a hybrid load. It shuts the load 3. So as you can see, just by manipulating some information which goes from one place to other place, the load 3 also is shed now. So this is so in the earlier case we have added a delay. In this case we have actually taken the uh, uh, in the earlier case it was more on the communication delay. We didn't take any information from the IEDs. We are just adding a delay to that. In this case we are intruding on the information coming from the IEDs, which is multiplying with 2, and it is causing that disruption. You can see how how that happens. Now let's go to the third case. Now, third case, it is a lot more problematic. Here, uh, it is again a packet modification, but uh, the user or the intruder again uh, hacks into that particular IDs, the messaging information, and adds a particular offset. So what is it doing? So as we know that the battery energy storage system, uh, it is used for smoothing out the power grid, the power fluctuations, right? Now what happens if the power fluctuations, how does the battery controller knows? Its controller and its inverter receives the information from MGCC, from microgrid control, and as well as its local control, right? So if I add a delay to the microgrid controller's input, sorry, if I add a offset to the microgrid controller's input, uh, because battery is not aware about what is happening on globally, it depends on the microgrid controller's response, microgrid controller's information. The battery thinks that okay, I need to discharge a bit more. So that is what is created here. The set point is manipulated, the battery set point is manipulated, and the battery starts charging, discharging, charging, discharging, and there are a lot of charge discharge kind of cycles happens. So the blue one shows when there is no attack, everything was good, the frequency was good, voltages was good, and fundamentally the battery active power was good. But when a offset was added, it starts discharging more, and fundamentally it has more oscillations on the frequency. Now, depending on um, uh, how much things get added up, it can cause a catastrophic scenario in terms of the tripping of the relays and so on. So these are again just three scenarios or example created, very simple examples created to show what is the impact of this cyber I mean, if somebody intrudes into a particular network, how they intrude is one aspect of it, which is what the EXATA CPS software does. So through packet manipulation and the algorithms and so on. But in a cyber physical system, so once when they intruded, what are some of the things which are possible, and which you can see it in real time. In the entire scenario, if you see, all these things are happening in real time. So the intruder can hack at any time and then go back and then actually create multiple hacks at different times, and the system can go to a catastrophic failure. Now, that is all with the example of a microgrid controller. I want to give a much simpler example, actually, uh, but on a slightly different application. This is on the tap change transformer. This is what we see daily. So now again, it is the same framework. I probably would not spend more time on this introduction, but what we have here, the earlier software we are using Hypersim because I am more interested in the power converter, the switching converter, changing those things and so on. Here I am using Phaser software because I am not interested in the switching level kind of application here. I'm looking more at a transformer tap change, which happens in seconds time. It takes a lot of seconds. So a phasor simulation is good enough for me. So again, is very simple network through a tap change transformer connected to a load and to a larger part of the grid was made in Operative software, and it is interfacing with the Exata software. It's the same here. So the tap change transformer uh, uh, is this entire model is kept in Opalati simulator, and you have a a virtual controller also. It has its own virtual IED, and that virtual IED is or virtual sensor. It is what interfaces with the Exata software. So and you have the rest of the SCADA, which actually emulating the SCADA system sitting here. So what is the application here? So normally, if you take any tap change transformer, the typical voltage ranges should be between 0.97 to 1.03 per unit. It is typically defined that, okay, if you are within this, if the output is, if this output of the sensor, controller sensor, if it senses the voltage is within this range, then no action needs to be taken. But if there is if the voltage is beyond this threshold for a certain period of time, then the controller sends in a corrective action. So what is the corrective action? The corrective action is to increase the stud of the tap change transformer, either upwards or downwards. I mean, there are plus 16 or minus 16 studs. So you either increase the voltage or decrease the voltage depending on the phenomenon, right? So that is the typical behavior. Now, if you see, the tap change controller depends on the information it receives from the RTU, from the sensors. Now, here is a case where the intruder intrudes into the sensor information of the RTU of the tap change transformers sensor, and has intentionally put a maintaining the voltage at say 0.96 per unit. Since this voltage is less than the threshold, the tap change controller, since it depends only on the sensor information, the controller thinks that something has happened, so it changes its stud. So as you can see above, okay, it changes its stud to increase the voltage. nothing has happened. So it increases again, or it changes the stud value, the position again, nothing happens, it goes on. And a typical system on the field typically has a particular threshold beyond which the what do you call it, beyond which the tap change does not happen. So eventually it blacks out. I mean, the system goes offline and it goes blackout. As you can see here, uh, the voltage was actually like maybe at 1 per unit only. Just by keeping that information of 0.96 at the sensor level, the the because it's a feedback control system, the controller keeps on correcting, tries to correct itself, and eventually goes to blackout. So this is a very simple example to demonstrate uh, the impact of the cyber physical system, or the impact of the cyber attack on a physical system and its impact on the overall network. So now, yes, so this actually paves way for multiple studies. Like, for example, as an electrical engineer, as I was mentioning, so if this creates me a platform to see, okay, if really somebody hacks into the network, and if he or she really changes the voltage to 0.96, and if I see that this particular stud has changed, not only the present in the present stage, the component has some vulnerability that can be very clearly seen. Now the logic says of the logic of the present controller says that, okay, look at the voltage and modify it. But if I'm an electrical engineer and when I start thinking, I understand that, okay, if the voltage changes or if the stud changes, the voltage has to change is one phenomena. It's not, it's beyond voltage change. There should also be some other phenomena that should happen in the power system if the tap change is working. So if I do not see any other phenomena, now that can be change in the signature of the signals or whatever, now that means I can see that either the transformer is not responding well or there's an issue with the sensor. So this gives us time to to do that additional contingency check, that is it really happening, or if something malicious which is happening. So these are the kind of studies which are possible once when we start doing that. So why I have taken so much? I know I have only 5 minutes, so I have only oh, I think this is my perfect. This is my last slide, and this would actually take me 5 minutes. So, so why did I talk so much about that? Because as we see, as I was mentioning earlier, so we are going more towards the smart grid side, and uh, the existing distribution network also is not going to be the same like what it was earlier or now. So there's more of smartness coming in. So um, now that smartness brings in its own advantages and disadvantages. So cyber challenges is one I won't say disadvantage, is one challenge that comes in. Uh, so we need to address those things. So that is one side. On the other side, there is also some positive or some new challenges in a positive way which comes in, which are like uh, the distributed energy resources can be used to provide ancillary services, like it can be voltage regulation, or perhaps maybe at some point of time even the frequency regulation at some point of time, or doing the demand response in a more automated way, and so on. So we this study or this test bed was developed in conjunction with US DOE and NREL and Argonne and others. So here the intention is what I talked earlier on the cyber side is one aspect of it. Now, uh, in the similar way, there are multiple things which are coming up, new different technologies which are coming up. How can we robustly analyze, study and analyze these things and impact of these things on tomorrow some other new kind of technology from in a smart grid might come up. So how can we study and analyze its impact on the network? So right, so for those things, it was thought that, okay, we need to have a a platform where called the Advanced Distribution Management System, where these different things can be co-simulated, studied, and understood. So what I am showing here very briefly is this has multiple objectives. On one hand, you have the EMT and phaser kind of simulation from OpenRT, and on the other hand, you have the OpenDSS tool. The intention is to show the co-simulation of multiple software. Now to this, probably in the future, we can add even the EXATA kind of thing. Communication network also can be modeled and embedded into it. So you have multiple software and multiple capabilities which can be studied at the same time. Okay, now the application here is the volt var control. So that is to manage the voltage and var reactive power within the network as the situations change. So how does the situation change? It depends on solar. We have a real solar inverter which is interfaced through a power hardware in the loop setup, which I talked about earlier. So which has a power amplifier in the between that gets integrated. Say for example, in this part of the network, it is a big network, and you have how do you control the volts and vars? You control by changing the tap change transformer, or you by controlling the capacitor bank, right? So, but if you see, there is an optimization needed there. So a capacitor bank can have only two states, on or off. But every time when it is on or off, a huge amount of surge goes through those capacitors. So it impacts its lifetime. So that's why all these capacitor banks, for that matter, even the tap change transformers, they have a reliability aspect attached to it, like how many operations can it do within its lifetime, so that it can survive. I mean, assuming even the situations are still perfect. I mean, the quality of the voltage, everything is good, but still, if it has so many operations, then it's probably, you can say, from reliability aspect, it comes to close end of its life, right? So we have this um, tap change transformer whose controller is a real hardware which sits here. In the same way, you have a capacitor bank whose capacitor bank controller is a real hardware which sits here. And all these systems are connected to a virtual SCADA system, and mimicking the data inflow and outflow. So what was done here? What was done here was, it was shown that two things: a load change and other phenomena were created, and it was observed first that what is the impact of these changes on the volts and vars on the one particular feeder. Okay, then it was shown that, okay, how the DERs, in this case the solar inverter, can actively contribute to improving the voltage regulation, or the supply the necessary reactive power to improve the voltage regulation at that point of connection. Okay, yes, there was a certain improvement. Now even then, beyond that, some control needs to be happened. So how should I switch on? Should I switch on my capacitor bank, or should I switch on my tap changer? How often should I do? Those were That optimization routine was run. So essentially, this has shown two things fundamentally: how this test bed can help in studying these various things, number one. Number two, how the distributed energy resources can help in providing the ancillary services. So a comparison was made, like, if a solar is not contributing to the ancillary services, how was the switching of the capacitor and transformer things, and how was the overall performance metric of the network, versus when the solar actually is contributing to it, how is the performance. So this was one application which was targeted, and it was done. So in a sense, this actually paved a way to become a vendor neutral test bed. And I believe my intention of talking about this in the detail here also is that from India perspective, from our research and from our Indian utilities discoms perspective, it is we are at the cusp of having more technologies embedded into our systems. So it is imperative that we have such kind of test beds at distribution companies or at the research facilities and so on, so that firstly, it paves way for a very robust research study and analysis, because the problems in India are different, from the problems or the issues or the scenarios in North America or Europe. I mean, we have predominantly weak grids and our I mean the loading patterns and everything of us are different when compared to others, right? So it's very important for us to have these kind of things, and you know, which helps us in making that you know, this study. So um, that's the reason why for me that's the reason why I put up this study. I think I just completed. If you want more information, this is, please go to that link below. I mean, it has a wealth of information. It is a it's a study of 2.5 years, I believe. So I tried to cover it in 4 minutes, but the intention was not to cover everything, but only to tell that such a kind of thing is there and very much needed. I think with this exactly on time, I come to the end of my my presentation. So if you have any questions, yeah, please feel free to drop me an email, or so I can definitely get in touch with you. And I might not know the answers to everything. What all I know, I can answer. If not, at least I can find out the answers and let you know. That, madam, I, I, I am end of my presentation, madam.
Thank
Wonderful,
you,
sir.
sir.
It's a
Thank you,
very
sir.
wonderful, it's a very
Uh,
wonderful. I mean, like sort of like a black magic. You know, we totally attracted everybody there. Your test bed
uh,
was a magnet which attracted everybody there. A wonderful lecture and very, very informative. And I am thinking, you know, there's a lot of research scope. I mean, as you said, possibilities of research is, you know, is there everywhere. I
Yes.
mean, you have you have simulated a cyber attack on
Mm-hmm.
a simple microgrid and all that, and to analyze that itself is a big subject.
Mm-hmm.
Really thought-provoking and mind-blogging, I would say. And people,
Thank you.
everybody says power system is all saturated. It is not.
Yeah,
Power
correct.
system, you know, it is just you know in the cusp of what we said like.
Correct.
So we have many things to do, especially with the in the inward, you know, I mean, sort of mingling and integration of so many other new technologies coming in. So we
Correct.
have to go with the sort of a time scale. That's why the real-time studies are required. It's a
Correct.
wonderful, wonderful topic, and it has really provoked everybody. Very
Thank you.
nice, sir.
Thank
Thanks
you.
a lot, sir. Thanks a lot.
Thank you.
Sir,
Thank
we
you.
have a couple of questions from
Sure,
the
ma'am.
participant.
Mm-hmm.
Priya Kumari ma'am, can you unmute yourself and talk?
Yes, ma'am.
Yeah.
Ma'am, am I audible? Yes.
Yes, ma'am. Please
Yes, ma'am.
introduce yourself.
Yes, ma'am. So, sir, I'm Priya Kumari from SRM Institute, Chennai, ma'am.
Mm-hmm.
Sir, my question is, what were the input that is given to the virtual ID? As you say that we can uh, model IEDs in e-phasers in, right, sir?
Mm-hmm. Yes,
So,
madam.
what were the input that is given that we are supposed to give it an IED? Because we are collecting like a physical grid, what you have shown, sir, that
Mm-hmm.
microgrid.
Mm-hmm.
From there, the inputs like the voltage and the
Uh-huh.
E and
Okay.
Q.
Mm-hmm.
So, what were the inputs we will? Because IED will come in the second layer, right, sir? As
Mm-hmm. Mm-hmm.
talked in IEC 61850 layers. So,
Mm-hmm.
bay level, mostly this IEDs were placed. So, what were
Mm-hmm.
the inputs we
Yes,
used?
madam. So if you can see this table here, um, the typical inputs which we give are, I think, the measurement points, the P measurement, Q measurement, and the status of the breaker and the RMS voltages.
And the output of the IED, sir, and how
Mm-hmm.
it can be reconnected back in simulation point of view, sir. So how we are giving the output of the IED? Am I directly giving it to the switch over there at the upper level, sir? As ID is placed in the bay level, so the
Uh-huh.
output of the IED, are we giving it
Mm-hmm.
to the upper to the process? Sorry, bay level, sir, or the station level, sir?
So you are talking about this, right?
Yes, sir.
Yeah. Yes. So it's a good question, madam. So there are two things here. Uh, so that's where the Exata software also comes into the picture. As far as we are concerned, we will define what is the particular node number and the node identifiers, and give it to this Exata software, that interface automatically gets done by the software, Exata CPS.
Okay, sir. Sir, this Exata software, is it equipped with Opal RT 4510? Because in my college, we have 4510, and when I attended the Opal RT conference, they suggested that we required a higher version to have that scalable technology. Is it
Correct.
so, sir?
Correct, madam. So, your question is like, can we use this along with 4510 4510?
Yes, sir. Like because like we have an Opal RT, and because
Mm-hmm.
we want to integrate a scalable technology as we have to work on cyber physical test bed. So is it not possible to have with the older version, sir?
Good question. Actually, very good question. Uh, I am bit doubtful, madam. The reason is okay. No, sorry. I am bit not doubtful. Opposite. I'm thinking it should be possible, but the question comes here is with this. So if you are taking this kind of architecture, right? So here,
Yes,
if you
sir.
see the Exata and the Power Grid were both simulated in different cores.
Yes, yes,
Now,
sir.
so do we have those many number of cores to put it is one question, and and also it
The
depends
last
on.
slide, the last slide of yours has having the 4510, sir. After this slide, the last slide, sir, where the email ID and you have given, sir. After this slide. The last slide where, sir, yes, sir.
This one.
Over here, yes, sir. Over here
No, no,
is
no.
the
Okay, this
Party
is
4510.
yeah, yeah, yeah. No, no, no. I know this is to honestly say this is just a marketing slide. I mean,
Yes,
this
sir.
was
Yes,
me.
sir.
Yeah.
In this core, I think four cores are there, sir. Right, sir? Opalati
I
4510, sir. Have four
four
cores.
five. It depends, madam. Again, it depends how many cores are activated. Actually, it has a
Okay.
maximum of 4 cores. So depends on how many cores are activated. I mean, like uh, I should say what we buy. Okay, depends on that how many cores will get activated. So I mean, honestly, I am from R&D side, so I do not know, uh, from what exactly architecture do you have and so on.
Sir, the
But
last question, sir.
yes, madam.
Sir, in Chennai, do we have this like scalable? Do any of the colleges is having right now functioning with new identity?
Good.
Because again, it's a marketing question, sir.
No, no,
Sorry.
no. Actually, it's a good question. I remember one of my salespersons was telling that somebody was interested. Now, did they buy it? I do not know. I can do one thing. At least I can find out and get back to you.
Okay,
But
sir. Okay.
yeah. So you are you. Sorry, ma'am. I didn't get your question. Sorry. Your name.
My name is Priya Kumari, sir, and my research. I'm a PhD student, sir,
Okay.
and my research area is based on a cyber physical
Okay.
digital modeling.
Okay.
So right now, sir, because we don't have a scalable with the OpenRT, so
Hmm.
in the MATLAB, I'm working with this OpNet, and we also have the OPC, sir. So
Okay.
externally, we are trying to integrate both the physical and communication system.
So can you do one thing, madam? So can you, I mean, of course, this is a generic email because the reason I give this email address is because I started getting many sales requests. So I again had to forward it to sales or marketing. So I thought, let me give directly the sales and marketing so that if it is comes to me, it comes to me. Can you drop an email exactly defining what you have? Okay, maybe it'll be good if you can give even your specs. I mean, for 4510 is just like I mean, if I can say on a loose terms, it's like saying Samsung M10 phone. But again, in M10 there is M10s, M10F, M10D. Some variations will be there, right? So if you can give your exact specification, like this is what I have my system in the college, and this is exactly what I want to do. I want to do this kind of study. Okay, so this is my specification. So does I am interested in the scalable, the Exata kind of thing.
Yes, because
So is it
attack
possible?
scenario I need to create, sir. So
Correct.
for sure, this scalable is, and now OpenRT has integrated with that, sir. Sir, before the scalable, sir, how the OpenRT was previously integrated with the communication part, sir? Like, because papers are there with the, as I say, OpNet modeler, OPC toolbox for the communication and the real-time simulation.
Honestly, I do not know because I joined much recently, so I
Okay.
do not know how they used to do it earlier. Honestly, so
Okay.
yeah, yeah,
Okay, sir. I'll drop on this mail ID, right, sir?
sure,
India at the
yes,
rate.
yes. I suggest like be as clear and thing as possible because we can see what can be done.
Oh, thank
Yep, thanks.
So very, very good interaction with the Priya and the speaker. I think wonderful. Like a lot of research areas can be touched upon.
Mhm. Yes, sir.
And I think you can interact with many people. Maybe they would. I will request anybody to send the emails to us. We can forward it to Shravan Kumar, or you can
Yes.
directly deal with him also,
Yeah.
and we will take it up to the next level.
Yes.
Really,
Sure, sir.
again, thank you, sir. Thanks a lot. It's really a good talk
Thank
of
you,
the
sir.
day.
I hope it is helpful for everybody, and
Yes. That is my thing.
Yes,
so
sir.
great.
Thank you, sir,
Yeah.
for
Thank you.
your insights on real-time simulations, various examples, the case studies. It was really interesting and thought-provoking. Thank you so much, sir.
Thank you, madam.
Thank you.
Thank you. Thanks. Thanks. Bye.
Thank you, sir. Thank you, Mr.
Thank
Abdul.
you.
And thank you. Thanks, Gopal RT, to depute you to our session.
Mhm.
This is
Thank you, sir.
really a good opportunity for us.
Yeah. Thank you, madam. Thank you, sir.
So,
Bye.